All right. Hello, everyone. Welcome to today's Corundum developer meeting. Don't have too much to talk about today, just a quick agenda. So real quick announcements. I'm just going to gloss over the project ideas that I've been presenting the last couple of times and then get into the status updates. All right. So announcements. The next Corundum developer meeting will be in 2 weeks on October 9th, assuming I've done my math correctly. And then the next Switch developer meeting will be on in 1 week on October 2nd. So if you're interested in Switch, tune in a week from today, and Carlos will talk about that in more detail. All right, so project ideas. I'm not going to talk about this in much detail today because this hasn't really changed much over the last couple of meetings. If any of this looks interesting to anybody, if anybody's got any questions, happy to bring it up during the discussion as a discussion point, or we can certainly take that offline to Zulip or whatever. But the idea here is if anybody wants to get involved in developing something on Corundum, these are some relatively self-contained project ideas that could be interesting to work on. All right, so again, not going to talk about this too much, but if this interests somebody, bring it up after the status updates as a discussion point, and we can talk about it. All right. So status updates. Over the past couple of weeks, there's been a handful of things that I've been chipping away at. Primarily Devlink support and PTP CDC modules have gotten some work as well. Then I have a slide summarizing, all the updates that have been committed to the development repo. I'm probably going to push that up to the main repo relatively soon. I'll certainly let you guys know when that happens. And then the other thing I've been doing a lot of chipping away at is potential updates to some of the PTP timing and timestamp handling components, as well as trying to figure out how all this is going to dovetail with White Rabbit style time synchronization. Trying to get my head wrapped around that. If we're going to integrate some of that functionality into Corundum at some point, what's going to need to be done in terms of groundwork, and then just real briefly go over some of the architectural changes that I have planned for Corundum. All right, so let's go through these one at a time. First thing, Devlink support. For those of you not familiar, Devlink is a kernel subsystem for managing various device resources. So I guess this was mainly put in place initially for managing, NICs, but at a lower level. So you can do things like change link types. You can switch between, say, Ethernet and InfiniBand link types. You can also modify the individual ports. You can create, delete ports. You can do port splitting. So this is used by a lot of switches where you have 100 gig ports or 4x25. So you could use basically the Devlink subsystem to flip the switch on that. So I think for example, like some of the Mellanox switches, or projects like Sonic that run Linux on switch chips, on switch hardware, they'll use this subsystem to manage some of that. There's also actually firmware update support through Devlink as well. So you get firmware update through ETHTool and firmware update through Devlink. I don't know too much about the differences between those two paths, but the Devlink support, I guess, since it's independent of the Ethernet interfaces, is potentially a little bit more flexible. And you can use it with devices other than Ethernet ones. I think there's also some health monitoring stuff. So Devlink's going to be necessary for handling splitting of 100 gig ports, both at the NIC level and at the switch level. Once if we get a switch working eventually, then we would need Devlink support for that. The side effect of adding Devlink support is it actually changes the network device naming. So basically, it adds this NP0 to the end of everything. And that's the N for the port name, and then P0 is just the default port names that you get from Devlink. But then if you split ports, then it adds an S something at the end. So you might have, so if you split, NP0, then you would get NP0S0, NP0S1, NP0S2, and P0S3 being the four, sub ports. So this looks like it's potentially going to be pretty useful. So right now, the implementation in the device driver in Corundum basically just registers everything. So there's some info calls and some APIs for actually looking at, what ports are available. But I don't have anything implemented right now to change anything. So I'll be probably building on top of that as things evolve. On the Linux side, the annoying thing is that Devlink is a hidden kconfig option. So there's actually no way to set it from any of the config files or anything. It's not visible in the UI. The option is ignored in the config files and whatnot. So it was a bit of a head scratcher to figure out, how to turn it on. So I ended up having to just enable the DSA, distributed switch architecture option, which is in the GUI, and then that turns on Devlink support. I figure, okay, that's probably a reasonable thing to do because, if we integrate the switch at some point, we're going to need DSA probably to make that thing work. I think there might be another option I could turn on if we don't end up using DSA, but it'd be nice if you could just turn on Devlink by itself. I don't know why the kconfig has to obfuscate that to such a level. Seems like the only other technique would be to patch some of the kconfig files to make it a visible option, and then you can actually turn it on. But anyway, that's not that big of a deal. It's more a question of how much unused code are you going to pull in. So there's DSA. I think there's also net device stimulator or virtual net devices or something is another option that can be turned on that also pulls in Devlink. I think those are going to be lighter weight than, say, turning on a Mellanox device driver or something. Anyway, so this is now integrated into the Corundum version in the development repository. It'll get merged back into the main one relatively soon. All right. So the other thing that I've been working on is improvements to the PTP subsystem, and the most concrete part of that is over the past week and a half, I've been trying to improve the implementation of the clock domain crossing components for PTP. So the intention here is to improve the sync performance and or reduce the area, and also to do this in a way to kind of prototype what's going to be used for the newer PTP subsystem. Question is, can we make this good enough for, say, White Rabbit, which has rather stringent requirements on the time sync? If it's not good enough for that, well, can we at least make it smaller? So I investigated a couple of new phase measurement ideas and did come away with some potentially interesting insights, but unfortunately the performance improvement was a bit lacking, and I think higher precision is going to require significantly more area, and I'm also just not sure if it's going to be enough of an improvement in terms of the precision to actually make it worth it, right? I don't think it's going to work well enough for White Rabbit without some additional modifications. So I decided to take what I learned and apply that to the current PTP CDC module, and get that all pushed upstream and whatnot. So let's see. One of the things that I noticed is I just took, so the nanoseconds field, it rolls over at 1 billion. So I put 999999999 into Python, converted that to hex, and the result, well, you'll notice it ends at 9FF. So that means that the lower 9 bits actually, they roll over naturally. I guess an alternative way of saying that is that 512 is a factor of a billion, which is kind of interesting. I didn't think you'd have that large of a power of 2 that you could pull out. So that means that, if you truncate everything above the lower 9 bits, then you don't need to deal with, what happens when the seconds field rolls over, which is kind of convenient. So what I ended up doing is adding another phase detector to look at bit 8 to compare both the source and the destination clock domain clocks, and based on that we can drive the PTP phase step size, or the PTP period register, and use this for kind of a rough phase lock, which will get very close actually. And then to improve the phase tracking, what we do is we simultaneously capture timestamps in the source and destination clock domain, truncate that just to the lower 9 LSBs plus the fractional nanoseconds portion, and subtract to get a a fine offset. And then you have a PID loop that adjusts the period register as a result to lock everything up. And the result of that is a savings on area, but basically the same level of sync performance as the current CDC modules. So the other thing is, since we're truncating at 9 bits instead of 16 bits, we don't need the rollover correction logic, so I removed all of that. And I also did some specific time optimizing register sizes and basically removing unnecessary LSBs. Like I matched the size of the integrator to the size of the period register. It doesn't make sense to have additional integrator bits if they're just being truncated off. And I also shrunk the actual phase comparison operation. So I used to look at all 16 of the fractional nanosecond bits. I truncated that to 4, and it doesn't seem to have any effect on sync performance. I think all of those additional bits are just not providing enough additional information. They just end up being noise. So truncating that off means that all the logic is a little bit smaller. I also removed the PTP sample clock option from Corundum. Just going to make that a requirement. I think you can just tie that if you don't really want to get the highest possible performance. You can just kind of tie that off to one of the transmit clocks or the PCA clock or whatever. It doesn't really make that much difference. But by requiring the use of that port, it simplifies the logic in the code or in the module a little bit, because then it reduces some duplication and whatnot. But yeah, the end result of this is that the module shrunk from about 800 LUTs or 816 LUTs to 636, which I think is about a 20% savings. And then flip-flops, it went from about 790 to about 697. So, that's a decent improvement. I think most of that is actually coming from effectively the PTP clock component and not so much the time synchronization components. So that's actually probably a good thing, because as I start working on the improved PTP timestamping and timestamp handling components, if we move to, say, like a truncated timestamp format instead of the full 96-bit format, then we'll get a much larger savings in the CDC modules. So all in all, that's looking pretty good at this point. So in terms of Corundum updates, basically updated the PTP CDC module, updated the Devlink support, and then there was also a potential bug in the DMA RAM DMUX module that was discovered by trolling through the Vivado warnings, and there was a bit of an assignment mix-up between blocking and non-blocking. So I don't know if this actually fixes any real-world problems. I know somebody was running into a crashing issue. Maybe this solves that. I'm not sure. So whoever's running into a crash, let's try the updated code and see if that helps anything. But this is in the development repo, and it'll end up in the core upstream repo relatively soon. All right, so moving on to some forward-looking stuff. So potential timestamp handling improvements. This is something that I've been kind of mulling over in terms of, how do we reduce the throughput, or not the throughput, the footprint of all of the PTP timestamping and time distribution components. So the observation here is that the MSBs of the PTP clock are basically constant. And when you're operating at high data rates and you're not holding on to packets for very long, well, does it really make any difference whether you're actually carrying around all of those additional bits? Or could you truncate them and then reconstruct them later? And then also there's two different PTP timestamp formats. There's a 96-bit format, that kind of absolute time of day format, and then a relative 64-bit timestamp format. Is it possible to support both of those with the same timestamp capture logic at the max, right? If you can construct the 96-bit timestamp from the 64-bit timestamp, well, maybe you can use both of them. And there's also some advantages of using the 64-bit format because it rolls over nicely. So if you need to do any math and modify the timestamps, it's going to be easier to use the relative timestamps for that. So, but you can use the relative ones that way and then convert those back to the full, 96-bit timestamps. That's potentially going to improve a few things. In general, whatever we come up with, it's got to handle, timestamps rolling over, right? When those high order bits do update, they have to handle that correctly. Multiple clock domains, and then also long wires, right? You might need to send the PTP time long distances across the device. I guess I already mentioned this. There's the two different timestamp formats. There's some advantages and disadvantages to each one. Ultimately, you need the 96-bit one for knowing the absolute time of day. This is the one to include in the completion messages and whatnot back to the device driver and the operating system. But there are some advantages to the 64-bit format, and it might make sense to find a way to make both work, especially because some of the math might be a little bit easier on the 64-bit timestamps, or potentially a truncated version of 64-bit timestamps. Right. So the original kind of thing that I was looking at is just doing MSB reconstruction, right? We're going to do the same thing that we're currently doing for the least significant bits, the timestamps, but we're just going to whack off the MSBs and then reattach them later. So my idea here is to split the timestamp to two pieces with a couple of, overlapping bits in between to figure out when there's a rollover and do the correct thing. Timestamp capture logic at the max is only going to handle the fine portion, which means you can lose all the MSBs and save all the blockgram bits and whatnot, and all the FIFOs and such that correspond to those. And then the coarse portion would be transferred via slow serial link to whatever components actually need the full timestamp. And then the hardware clock, the master clock, would shift out two coarse timestamps, the current one plus subsequent one, and then the reconstruction logic would store a handful of timestamps in distributed RAM indexed via the overlap bits, and then the reconstruction would be just a simple table lookup. So very, very small and simple. But after thinking about this for a while, it's like, well, okay, maybe it makes sense to, because this would still use the existing kind of parallel interface that's used for transferring the PTP clock across the device to all of the Macs in the first place. So got me thinking, well, maybe there's a way to simplify this a little bit and transfer PTP time just over, a 1-bit serial connection. And then instead of driving a, 64-bit or 96-bit or something bus to each port, well, we can just drive a 1-bit wire. That could potentially result in some significant area savings and potentially reduce routing congestion and whatnot. So the idea with this is to run PTP reference clock to the whole device, the global clock network, and then to run the hardware clock, the master clock, ahead by some number of clock cycles, and then use a faster serial data link. And so instead of something like SPI running at megahertz or something, the idea is that this would run, the bit clock would be the PTP reference clock. And then we would send data synchronous to that clock that includes, information to set the PTP clock. I think the allusion that I made before was to the the old style talking clock. I don't know if you remember the days you had a phone where you can punch in a number and call somebody, not with a cell phone, but the actual thing sitting on your desk. And you can call either like a standards organization or the phone company that would have a talking clock. The way it works, you dial it in, it says there'd be a recorded voice at the other end just continuously reading out the time. So it'd be like, it's currently 9:24 and 0 seconds at the tone, doot. And then the tone indicates, that's the valid time. So it kind of tells you what the time will be, and then there's a tone. So the idea with this serial protocol is you do the same thing. You have all the information necessary to, set the clock, and then you have a reference edge that's used to, latch it in. And one thing that I'm thinking about doing is actually running this even earlier. So maybe 32 cycles earlier or something like that. So the reference edge is not sent on the current time. It's sent, 32 cycles early. And then that means that you have a few cycles to compensate for pipeline delays. If you have to load the clock a cycle or two early so it will propagate through internal registers, then you can do all that sort of stuff such that 32 cycles after that edge, the described time gets clocked out of the PTP leaf clock module. So that's kind of what I'm thinking about here. And potentially there's other information that can be transferred over this serial protocol as well, such as, for example, the full 32-bit, step size, the full, drift information. If you're running in kind of a coherent setup, that's going to be necessary for a few things. And also you'd have access to, the full fractional nanosecond value, not necessarily truncated at 16 bits, like you would have for the, normal timestamp format. So that could potentially be useful for certain applications. But yeah, so I'm starting to sink my teeth into this a little bit and figure out kind of what this is going to look like more concretely. So like I said, I've been doing some work on the PTP CDC module, kind of going in this direction to get some of the groundwork sorted out. And this also dovetails with the White Rabbit as well. So the other thing I did over the past week or two is to take a look at some of the White Rabbit documentation to figure out sort of what they were doing in the in their reference switch and how we might be able to do some similar stuff in Corundum. So the original White Rabbit reference switch, they basically take the complete brute force approach, and they run everything synchronously at 125 megahertz, which, you can get away with that at, gigabit Ethernet at 10G, especially if you want to support 10G and 25G. It's a slightly different story. I think we're going to have to take a slightly different approach. But the idea with the White Rabbit switch is, since everything is synchronous at 125 megahertz, the transmit timestamps are basically by definition accurate. And then the receive timestamps, those have to be fixed up basically in software. So they use the DDMTD high resolution phase measurement to determine the phase offsets of all the RX clocks. They get phase locked, with PLLs at the other end of the link. So the frequency is going to be the same. It's just a phase offset that has to be measured. And then the software, it'll take a look at the output of the DDMTD and convert that to, fractional value extension for the actual timestamps, and then factor that in. So in terms of what we're going to have to do for Corundum, the situation is slightly more complicated, I think. So the first thing is we got to make sure that the latency of the physical layer stuff is as predictable as possible. So this means using synchronous gearboxes, either using the ones built into the transceivers or fabric gearboxes outside of the transceivers, or maybe even a combination of the two. And I have some ideas on the Mac and Phi level to support using the synchronous gearboxes, because right now it only supports the asynchronous gearboxes. And the latency of those, actually, I don't know how predictable the latency is, but they use multiple clock domains, and the fewer clock domains, the better, I think, in terms of getting the kind of precision that White Rabbit requires. So that's going to be one thing to get sorted out, is how to make these things operate in using the synchronous gearboxes. I think this will also improve the latency slightly as well, but that's not as important as just having a predictable, consistent latency. The other component here is that running the transceivers in different modes is going to require running with different internal clock frequencies. So if we're using the synchronous gearboxes instead of the async gearboxes, then the frequencies are going to be 161, 322, and 402, plus a bunch of junk after the decimal. So 161 will be for 10G, 322 is what the CMAC uses at 100G, and then 402.83 is 2.5 times 161. So the interesting thing is that these are more related than you might think. They're all integer multiples of this 80 megahertz number, right? Times 2 times 4 times 5 will get you these guys. If you divide that by 2, then you get even integer multiples, which is potentially a requirement under certain circumstances. So this has got me thinking, well, what if we use one of these, this 80 megahertz or 40 megahertz as the reference clock for the PTP time. And then we distribute that to, all of the ports, and then use DDMTD for the phase measurements. Because I think what we could do is divide down, the Mac user clock effectively by, 245 or 4810, depending, and then use the DDMTD to make the appropriate phase measurement. So I think that could potentially work. I don't know if there's going to be any other modifications that are necessary to the CDC logic for this to work, because I think when you're operating in kind of this this synchronous mode where the clocks are related, that's going to be a potentially a slightly different mode of operation versus just normal when everything is fully asynchronous. So that's, I think, going to require a little bit more ruminating. But another component of this too is, PCI Express is totally unrelated. So if you want to sync the time back to the host clock with high precision, that may require a slightly different approach, right? Because that's a 250 megahertz clock from a totally different source. I mean, I guess as it stands right now, without PTM, it's probably not really worth doing anything more complicated. But say if you have PTM support, does that require doing anything at a higher level of precision? Not sure. It's probably going to require a little bit more thought to get all the details figured out. Although I guess I wonder, could you modify the host motherboard to slew that clock and then bring it into alignment that way? Yeah, that's probably not feasible. Anyway, so that's another thing that I've been mulling over a little bit. I don't know if anybody has any ideas and related to White Rabbit, but this is something that I'm starting to chip away at.
I guess one important thing, Alex, is that if you're doing some division of clocks, you always have to keep track of the dividers. So if they are out of sync, then you have an offset somewhere.
Right. Yeah, that's true. That's true. Yeah. So if we're talking about doing this, a divider associated with DDMTD, I think is probably not going to be a major issue. I mean, this was something I was trying to figure out anyway, right? If you have two clocks that are running at different frequencies, like how do you even define a phase relationship between those? If the frequencies are the same, okay, that makes sense. But if they're different, then it's like, how does that work? So if we're doing the division, in the fabric, then we might be able to, just use the divider value directly as part of the phase measurement, delay measurement process. But yeah, that's definitely a very important consideration. And that's, I think, one of the things to worry about in the serializers as well. I think there are some issues with some of the internal clock dividers not necessarily booting up in the same state. So
yes.
if you want to get predictable latency, that's you kind of have you're playing roulette or something. Every time you power it on, it's going to come on in a different state. Or every time it comes out of reset, it's going to come out in a different state, in a different latency. So I think there are some provisions for adjusting that in the modules or something in the transceivers. That's not something I've looked into, but I think that might be something we're gonna have to look into as well. It might be as simple as just turning on a configuration option. It could be something more complicated. But yeah,
and it depends on the transceivers as well. So I think White Rabbit kind of fires the reset until the specific divider comes up.
Yeah, I was thinking that is an option. You could just
It's
keep
pretty
resetting
reliable
until you get the divider you want. Yeah. Yeah,
so it's not like hundreds. It's not like thousands of options. It's more like 10 or something, and
it's
it's a
based
very
on
short.
it's based on the ratios, right? So if you have so they're running just with a 10-bit, well, with the original White Rabbit switch, it's just a factor of 10 serialization. So yeah, there's just 10 options. So how many times do you need to reset to get the right one? Well, actually, I guess potentially quite a few, but the probability that you need to do more is that falls off. So but but yeah, for Corundum, we'd be talking about 64, 66 bits potentially. So you might need to reset it a few more times. I'm not sure. That's definitely worth some poking at. The other thing I noticed is with the White Rabbit switch, they had a whole bunch of calibration components to basically bring the output of the serializers back into normal I/O pins. They had like some sort of crossbar chip on there or something that they could use for that. I think to handle this strangeness maybe with the PHYs, just to make sure that the delay is known. I mean, obviously, we won't be able to do that with any of the FPGA boards. In a runtime sense, we might be able to do some stuff for debugging, but on the workbench, you can hook stuff up however you want. So, I guess we'll have to see about that, right? Because if we have to reset until we get a particular phase offset, how do you know what the actual phase offset is, right? So yeah, that we'll have to cross these bridges at some point. The one aspect is getting the transceivers and whatnot to do what they need to do. The other aspect is kind of integrating this into the rest of the design and figuring out reference clocks and phase measurements and whatnot and how this is going to work on that side. I guess the other aspect of this is I'm not even sure how well White Rabbit's going to work at 100G, with CMAX. Obviously, I think you can probably do Syncy with those. Just take lane 0 or something and synchronize that. That shouldn't be a big deal. But getting the very precise alignment of the starter frame delimiter is a slightly different story. I'm not sure how to extract that information out of the CMAC. So anyway, I think the priority is to get it to work at 10G and 25G. So 100G, I've just been putting the clock down just to make sure that we have all our bases covered, but it's unclear if that's actually going to work. Anyway, stuff to ruminate on. And then I guess real quickly, I have the slides here talking about some of the architectural changes that I want to make to Corundum going forward. First one is consolidating down to a single hardware interface, especially with smaller devices and with some of the changes that I want to make to make kind of a performance versus area trade-off to increase the performance at the expense of increased area and some of the queue management logic. I think it's going to make sense to try to reduce some of the duplication, where if you have a board with 2 ports or with 4 ports, you don't necessarily want to duplicate all the queue management logic 2 or 4 times, especially with some of the modifications that I've made to support more software management of the queuing resources and whatnot. I think it's going to make sense to move to having a single hardware interface, and then having software present that as multiple OS level interfaces and manage all of the resources appropriately. So I've been looking at the design to figure out, basically what needs to be done in order to support using, multiple ports per interface, and exposing those as separate ports and supporting that upstream, and then, making all of that work reliably. So there's definitely some modifications that I think need to be made to some of the queuing infrastructure to support this. And then also potentially some modifications to the scheduler, so we don't need to have one scheduler per port, but maybe we can have scheduler modules that are capable of working for multiple ports. So that still kind of remains to be seen at this point, what modifications are going to be necessary exactly. And then also, if at some point we include an embedded switch of some sort, it's going to make, I think, even more sense to manage all this kind of stuff in software, especially using the Devlink interface and whatnot. So we have the Devlink interface there. We have a lot of the building blocks and base components that are going to be necessary for this to work. So we just have a little more fleshing out to do. Next thing is the switch integration and kind of the implications for that on the rest of the design. For sharing code between the NIC and the switch, that's going to open up some interesting possibilities. Things like splittable ports, Well, I think well, one aspect of this is how do you control it from software. Devlink is, I think, going to be the way to go here ultimately. And then, how do we handle that in terms of the application section interfaces? Not quite sure at this point. If we're using the eSwitch for, SRIOV and whatnot, well, could we add additional ports for the application section for its dedicated use? I think that would be a very reasonable thing to do. And then also, what does this thing look like from a clocking perspective? Would the application section interface need to change? Would we decouple anything on the PCIe side? And also looking at all the clocks for White Rabbit and potentially some of that sort of thing, it also has me wondering about, well, would it be possible to couple some of this stuff more directly to the link clocks, right? If we're using multiples of, this 40 megahertz or 80 megahertz or whatever, maybe we can generate some more nice clock frequencies. Well, I don't know about nice. The numbers probably wouldn't be very nice, but it would be nice in terms of being ratios of, the Ethernet clocks that could be used, say, for the Corundum core clock or, the switch core clocks. That would be more directly related to the Ethernet line rates, such that, if you lock everything up by a sync key, you might get more predictable performance if the whole switch clock is running synchronous to the links in some way. So that could affect things a little bit as well. If we're going to integrate a switch. Let's see. I think the last thing I got here is the application section pass through. So this was something that MLE brought up. Some applications require more stuff to get passed through the application section from the top level. So if you're working on an FPGA, you could be adding, additional interfaces for, whatever, maybe your RF related stuff that you got to pull in, or, it could be any number of things. It would make sense to have some kind of provisions for connecting that through to the application section. Obviously, it's not going to work on all the boards. It's only going to work on, individual designs that are more customized. So it doesn't really make sense on like an Alveo board that really doesn't have any additional I/O, but it could make sense on, another dev board, or a, custom board that has FMC connectors or a Zinc RF SoC or something. So, it would be an option to add a bunch of additional AXI stream or AXI interfaces or whatever, but it might make more sense to go in the direction of, well, maybe we have some macros that can include some information in the port definitions and whatnot. So I think the folks at MLE are going to take a pass at this and see if there's a nice way to do it with macros. But on the flip side, maybe this is a good argument for taking a more serious look at, converting to System Verilog, right? Because with System Verilog, you could just pass through, I think, kind of a generic interface that then you could override with a different definition during the build process for the application section. So potentially a couple different routes to take here, but yeah. Or
yeah, maybe. Yeah. So we just started to look at this. We put together a first example, and it at least goes through Vivado.
Okay.
And to make to get a better overview about the support of various compilers, we want to do a very minimalistic example, and then run it through Ada Playground and test it with a couple of additional compilers, because it
okay. So not
seems
necessarily
as if
to modify Corundum
macros
itself, but just to put the ideas together in a simplified, minimal example, and then try it out on several compilers and make sure it works. Right. So I guess we're not just talking about. So I guess we're talking about both simulation tools and also the build tools. So EDA Playground, does that allow you to do synthesis tests, or is that just simulators? Because I mean, it's one thing to test it with Xilinx, Vivado, and the Intel's Quartus software, see if it builds. But then also testing with simulators, that's also important.
Yeah, I think it's mostly about simulators, but actually not sure. So I haven't used it a lot, but we will have a look, and I guess in a couple of days we can provide some input on this topic.
Yeah, okay. Yeah, I was thinking another potential way to do it is to kind of turn the design inside out, I suppose, and then put all the application section interface at the top, which is not clean, but it is potentially an option as well. But yeah, if we can figure out a way to get a pass-through working, I think that's going to be probably the most straightforward solution, even if it's a bit messy.
Yeah. Oh, well, the inside-out version might be more flexible. I don't know.
Yeah, it might
But
be
then
more
you have the
flexible, but they're
same
already
thing.
right. Yeah.
You have to push everything through all the hierarchies again, although it's more static, maybe.
Right. Yeah. I mean, I guess the other thing is that you have some ordering concerns as well. Like right now, I think there's a bunch of stuff that kind of gets computed in the in the MQNet core module, and determining signal widths and a few other things. So if you were gonna invert the whole thing and pull all the ports out to the top, there's a question of how some of that stuff would be computed, right? Because you'd have to compute it at the top level, and then I guess just assert to make sure it's correct. I don't know. It opens up a few cans of worms potentially. Anyway, I think that's about all I got. Yeah, that's all I got in terms of updates for today. So if there's anything people want to bring up for discussion, then we can certainly do that. Ulrich, did you want to say something?
No, that's fine, I guess. Let's stay with the current structure and see how we can push something through the hierarchies, and
yeah,
if we can still later on get everything wrapped around differently. So, but I guess we need to, for our current task, I guess that's not an option to put everything inside out.
Right. Yeah, it's that has its own can of worms to deal with. So yeah, I mean, I was actually kind of scratching my head over the system Verilog thing recently. Is that it seems like Xilinx has at this point completely discontinued all the 6 series stuff. So, and I mean, we haven't really been doing anything with the Vertex 6 hardware that we have at UCSD either. So, I don't know. It seems like it might be worth thinking about a conversion to system Verilog. It would mean dropping support, in the Ethernet repository for all the 6 series devices and whatnot, unless there's a way to, convert system Verilog to Verilog or something such that it can be built with ISE. I don't know if anybody knows of any tools to do that. Is there a way to convert system Verilog to Verilog for use with legacy tools? I don't know. I'll have to take a look at that. Because yeah, that would certainly simplify this last thing here, right? If we could just use the system Verilog interface and you could just stick whatever you want in there, then that would remove the need to do any macros or anything. Anyway, stuff to think about. Does anyone else have anything they want to discuss or bring up? I guess not. All right. Well, in that case, I guess we'll go ahead and adjourn the meeting for today, and we'll see you guys in 2 weeks or in 1 week if you're interested in the Switch development.
Thanks, everybody. Have a good evening or day.
As the case may be, or good morning. I mean,
Yeah, right.
Time zones.
Thanks, everyone. Bye-bye. See ya.
All right.
Thank you. Thanks,
See you guys later.
Thank you. Bye.